everyone, I am Sneha from the Web3 Compass, and this is day 20 of 30 days of building with Solidity. Now, we're particularly always very excited, but we're extremely excited for this particular day because we are going to deal with reentrancy attacks today. And what we're going to write is a FortKnox contract, and we've named it as FortKnox the reentrancy heist. Now, I don't know how many of you are aware of it, so if you're not, you can search about it. But then, me and Setu are extremely excited, and we're going to do something absolutely fun today. I hope you guys find it fun too. So let's get started. Now, everyone who's not aware about what this campaign is, go to our previous videos or go to web3compass.xyz. This is where you find all the details regarding the campaign. And this is day 20, right? And as mentioned, we're writing FortKnox.sol, where we're building a secure digital vault where users can deposit and withdraw tokenized gold or any valuable asset, ensuring it's protected from reentrancy attacks. Imagine like you're creating a decentralized version of FortKnox. Users lock up tokenized gold and can later withdraw it. But just like a real vault, this contract must prevent attackers from repeatedly triggering the withdrawal logic before the balance updates. You will implement the nonReentrant modifier to block reentry attempts and follow Solidity security best practices to lock down your contract. In this project, we'll show you how a seemingly simple withdrawal function can become a vulnerability and how to defend it properly. So let's just get started. I'm so excited. I hope I can just keep up to this excitement. I don't know. We just really enjoyed, working on this. So we are going to create two files. One is GoldVault.sol and the other is GoldThief.sol. Okay. Now, zoom in. Okay, great. So, we know that you've made it this far. You've learned how to write smart contracts, hold funds, transfer it, restrict access, delegate behavior, and all of that. But now we're about to enter the real battleground of smart contract security before we start diving into real world decentralized application. So let's talk about a very classic trap that caught even the best of us, which is reentrancy. Now imagine that you're building a ultra secure digital vault. Okay. Think of it like a crypto version of FortKnox. People can walk in, deposit their tokenized gold and walk out whenever they want to, withdraw it, nice, clean, simple. But then a clever attacker shows up. They figure out that the moment the vault sends them their gold back during withdrawal, they can sneakily jump in and ask for more before the vault realizes that they've already been paid. So suddenly, what should have been a single 1 ETH or 1 gold withdrawal turns into multiple ETH getting siphoned off in just one go. This, friends, is the famous reentrancy attack, the exact kind of exploit that drained tens of millions of dollars during the DAO hack of 2016. So you can read more about it online. But what exactly is reentrancy when I talk about it in layman terms? So imagine a vending machine. You put in a coin, press the button and wait for your snack. The machine first checks if enough credit is there, then gives you the snack and finally updates your balance. Now, imagine if there was a sneaky little trick that right after the machine gives you the snack, but before it updates your balance, you press the button again and again and again. Each time the machine still thinks you have credit because it hasn't gotten around to updating your balance yet and checking that credits again, right? So what is the result? Free snacks forever. I mean, not forever, but then at least till the time you're not tired of pressing that button or you empty the entire vending machine. So that is reentrancy in the smart contract world. Okay. So what actually happens in the code is that let's translate this vending machine story to Solidity. Now, you call a withdraw function on a contract. The contract sends you ETH using .call value, which we've written a lot of times. If you don't know what it is, go back to our previous videos. Again, I've forgotten which video is it that I actually talked about it in detail, but yeah, you have to actually look into all of them for that sake. Now, but you, being sneaky, have written a fallback function in the code, a function that auto triggers when receiving ETH. So inside the fallback, you're calling withdrawal again. So the original contract hasn't updated your balance yet. So it still thinks you have money because the last time it checked, you had money. So it sends more ETH. Now your fallback calls withdraw again and so on until the contract is completely drained. Okay. Now, why is it called a reentrancy? Is because you're re-entering the same function before it finishes the first run. The function is halfway through doing something very important like updating your balance, and you sneak in through the back door and run it again while it is still working. So it's like opening a bank vault, handing someone money, and before you shut the vault, they barge in and asking for more over and over until they wipe it all away, right? So what you will build today is a hands-on hacker style. So to really get reentrancy, we're not just going to explain it in theory and move on. We're going to do something better, something which is Web3 compass style, which is again putting everything to the building game. So we will build a working contract, simulate an actual hack, and patch the vulnerability step by step. So you will go from a developer to a hacker to a defender all in one go. Let's break it down. Okay, so the first one is going to be the GoldVault.sol, which is the digital FortKnox, and this is going to be your main contract, which is the vault. User can deposit ETH into the vault. Think of it as storing digital gold. Later, they can withdraw that gold anytime. We'll first implement a very basic withdrawal function, no guardrails, no protection at all. And then we'll walk you through how an attacker can abuse this vulnerability to drain the contract. Once you've seen it break, we will show you how to lock it down using a simple but powerful nonReentrant modifier, a custom built defense mechanism that acts like one at a time security lock, and by the end of it, your contract will go from wide open to FortKnox level secure. Okay. And the other one is the GoldThief.sol, which is again the attacker contract. This one's fun. You'll actually play a villain for a bit. This contract is built to exploit the weakness in Gold Vault. So it will use a sneaky little fallback function to re-enter the vault mid-withdrawal again and again. You will get a front row seat to hack how it works, how it drains the funds, and how fast that happens. And then we run the attacker after we apply the fix and watch it fail. Okay. Nothing teaches security like watching your own contract get hacked. Glad that we're doing a demo one and it's not a real world application that you're building, and then stopping the hacker in their tracks. Okay. So by the time you're done, you won't just understand what reentrancy is. You will know how it works, how to exploit it, and most importantly, how to prevent it. This is where you level up from just writing Solidity to actually defending it. So let's, get started building the digital vault and making it unbreakable. We'll first get started with GoldVault.sol. Every day when we're writing multiple contracts, I end up writing the entire contract in the latest file that was created. So today I'm not going to make that mistake. So yeah, let me just quickly copy this. Okay. And while I write all of this, you tell me that what is your understanding of, how should the entire state variables and all of that going to look like? What do you think? Think of it. Pause the video for a while. Think of what all we would need for this contract as a straight variable while I do my usual. Okay, so great. I hope you have, done a little bit of thinking. So the first thing I can think of is a few variables where we're saying, okay, we're making this one, private. And we're saying we need status, which is a private variable that tells us whether a sensitive function, like say withdraw, that we'll write later, is currently being executed or not. Okay. Then we'll write another private one which says, it's going to be a constant. We're saying not entered value equals to 1 means the function is not being used right now. It's a safe to enter. Again, entire hacker mode. Oh, okay. And then we're writing another private constant, which is going to be entered value equals to 2, which means someone is already inside the function block reentry. Okay. Yeah. Private entered equals to 2. Okay, great. Now we would also need a mapping where every address will be mapped to a UNT256 value, which is ideally will be our ETH balance, but then here we are going to call it as our gold balance. Okay. So we're saying public gold balance. Okay. Now what we're doing is that we know that we're building a digital lock. Before we let someone run a sensitive operation like withdrawing ETH, we check, hey, is this function already being executed? If yes, block it immediately to stop any sneaky second entry. If no, we flip the switch to, the variables that we have declared, which is entered, do our work, and then set it back to not entered once we are done. So this lock gets activated in our non-reentrant modifier. We look at that, next. Okay. So we will write our constructor and we will quickly move to the non-reentrant modifier here. So we're saying, okay, constructor, we're saying status will be equals to not entered. Okay, yeah, this has to be by default. Okay, now it's time for the modifier that we were talking about. So we're saying, this is why I hate writing constants. I'm always in the caps lock mode then. Okay, we're saying non-reentrant. Okay, so what happens here is first we will check the status. If the status is not equals to entered, right? Great. Otherwise, you say, oh, reentrant call is blocked. Okay, so entrance restricted or whatever you feel understood. And then we're saying, okay, status is, what's wrong? Status is, I'm too happy today. It's going to be entered. And what we do is we let it run and then we change the status to not entered. Now we did not close the constructor here. That is why it's showing an error. So now what happens here is that we've never really done this. In modifier, we generally write the condition. If there's a required check or whatsoever, we write the condition and then we go to the underscore. There's nothing literally after that. But this modifier here is like the core defense that protects the contract from reentrancy attacks. And it's like a do not enter sign that goes up the moment someone steps into the room and only comes down once they've left. So here, that is why we're writing like two conditions. So the require statement for you is clear. Then you are flipping the lock on with underscore status is equals to underscore enter, which marks the function as occupied. So we're basically saying, all right, we're going in now, lock the door behind us. So this prevents any nested calls from entering again until we are done. Then we run the function logic, which is what this underscore actually represents. We have already talked about it before. So we are saying maybe if you're writing safe withdraw, that function will run, or anything else which is guarded by the non-reentrant. And Solidity, that underscore is again replaced by the function code during the execution. And once that's done, we are putting the status back to not entered, right? So after all the ETH has been transferred, after all the balances are updated, we reset the lock so future calls can proceed normally. Now, why it works is because this modifier ensures that only one call at a time happens, and it happens inside like a protected function. So even if an external contract like an attacker's fallback function tries to call back into the vault, they hit the lock and get blocked instantly. Now it's super simple but super powerful as well, and it's your first real defense that we're talking about. So now let's get to writing certain functions here. Okay, so the first function is going to be like no function deposit, right? Now this is very simple. Everyone should be able to do this if you've been following us for the past 20 days, right? And we're saying, okay, so we're saying require the message dot value has to be greater than 0, right? If yes, great, proceed. Otherwise, deposit value has to be more than 0. Okay, and then we say, okay, once that's done, you have to update the gold balance of the message.sender with plus equals to message.value, right? Again, very simple. User sends ETH to this function. It gets added to their gold balance or contract. Now holds their funds until they withdraw. Okay. Now we'll write another function called vulnerable withdraw, which is again the function where things will intentionally go wrong because we want to see how, things are working behind the scenes. Okay. So yeah. Function vulnerable withdraw, right? Okay. So what happens? We're making this external, okay? And we're saying that UN256 amount is going to be the gold balance of this particular message dot sender, okay? Now, if the amount is greater than 0, great, right? Otherwise, you have nothing to withdraw, okay? We don't need this dot, but yeah, okay, nothing to withdraw. Now we will do the call function that we were talking about. So we say bool success message.sender.call value amount, and then because we are making the call to a contract, we don't need the encoding. Again, we have talked about this call function so many times in our previous videos. So that is where you're supposed to actually, go and check. So we'll check for success and we say, great if we get success. Otherwise we say ETH transfer failed, not dialed, failed. Okay. And then what we do is we say gold balance message.sender equals to 0. Okay. So at first glance, this looks totally fine. You check the balance, send the ETH and set the user's balance to 0. But that one small detail, the order of operations, is where the trap lies. So now let's look into what happens. Okay. So in the first function, right, we're saying that let's say a malicious contract calls vulnerable withdraw. But unlike a normal user, this contract has a sneaky little receive function, one that automatically triggers when, vulnerable withdraw call is made again, and the moment it receives ETH, right? Because we've talked about this, that receive function gets automatically triggered when you are dealing with Ether, like sending Ether, but you don't know which function to call, right? So now what happens here is that when you're checking the amount, gold balance dot message dot sender, and you're checking amount is greater than 0. So the user might have just one ETH stored in the vault, right? Now we send the ETH back to message.sender through that bool success message.sender.call value amount. But here's the twist. If message.sender is a smart contract, its receive function gets triggered as soon as it receives ETH. And inside that receive, it calls vulnerable withdraw again. So now we're back inside the same function before we've updated the user's balance, right? Because there was a require, and then the balance was getting updated through gold balance message.sender equals to 0. So it will say withdraw again and again and again, since we haven't hit this line at all, right? So the attacker balance still looks like 1 ETH. So when the reentrant call checks their balance, it passes again, and the vault sends another 1 ETH, and then the receive function gets triggered again, and the cycle continues. So this loop drains the vault before it even gets a chance to zero out the attacker's balance. Okay, now why is it dangerous? Is because external call is made before the state is actually updated. The attack re-enters while the vault is still in the middle of processing, and ETH gets drained multiple times from a single balance. Okay, now what we'll do is we'll write another function called safe withdraw, and we will add the non-reentrant modifier to that. Okay, so we're saying function safe withdraw, right? And we're saying it's external but with the non-reentrant modifier, and we're saying UN 256 amount is equals to gold balance message dot sender. Okay, I'll just copy these lines. So we do everything here same, with a twist. We are not doing everything same. We are checking the required amount greater than 0, nothing to withdraw. We'll still talk about the message.sender.call value. We'll still talk about require success ETH transfer failed. But this line that we've written at the end, we're going to check first. Okay, so this is going to be a secured version of our withdrawal function, the one that shuts the door on reentrancy attackers. So now let's break down what changed and why it works. I know that it's already clear for you guys, but for anybody who has not understood this, you need to know that we're checking the balance, and this line happens before we send any ETH. So that means the moment the withdrawal begins, we've cleared out the user's balance. So even if the attacker tries to re-enter the function, they will see the balance is 0 and the withdrawal will fail instantly. Now this change alone breaks the exploit loop section that was draining the contract in the vulnerable version. Okay, now there is a second fix where we're saying, okay, on top of fixing the order of operations, we've added an extra layer of defense here, which is the non-reentrant modifier. So what this does is that the moment someone enters the function, it locks it down. So if the same address, for example, any external contract tries to call it again, even through a fallback, it gets blocked immediately. Once the function finishes execution, the lock is lifted again. And that is what we implemented here. Right? So the moment you enter it, great, the lock is on. The moment you're done with the function, the execution and all of that, the lock is, back open. So even if we forget to set the balance to 0 as we did in safe withdraw, this lock alone could have still stopped the attack. Okay. So now, you have to remember the check effects interactions pattern. So now it's a very well-known practice called as check effects interaction. So check condition effect changes to state. That means when we are saying that this is like the requirement condition, right? And this is the check, right? This is the check. This is the effect. That means, are there any changes to state that is happening? And then you interact with external contract. And that is why check, effect, and interactions. So by the time we interact with the outside world, which we have no control over, our own contract state is already safely updated. And this avoids a whole class of vulnerabilities altogether, not just reentrancy. Okay, so we're done with this particular contract. We can just go compile GoldVault.sol and also very quickly deploy it so that we have the address. And now we will go to writing GoldThief.sol, which is going to be our reentrancy exploiter. So again, for learning only, for everyone who's watching these videos, for everyone who is referring to this document that we... Okay, so before we actually start with the entire thing, we have to set up the interface as well. Okay. So now what that interface is going to be about is, we should be able to interact with the vault. It needs to know what functions are available and how to call them. And that is where interface comes in, right? We've talked about interface as well before. So we're saying vault, right? Now there's function deposit. So we'll quickly write what's already there. Payable. Okay. Then we are saying function, what was it? Vulnerable withdraw, right? So because we are later going to, interact with this one. So we're saying external, and then we're saying function, safe withdraw, right? That was it. And then we're saying, okay, that is also external. Okay. Now, again, a very quick analogy. I think when we talk about interface, it's like a menu at a restaurant. You don't need to know how the chef makes the dishes. You just need to know what's on the menu, function names, what ingredient it has, which is the parameters, and what you get back. Like if there's return types, all of that. So in Solidity, an interface is basically a lightweight contract definition that includes only the function signatures, no implementations. Now, why do we actually need this? Is that our Gold Thief contract wants to call deposit to send ETH, vulnerable withdraw to trigger the attack, and safe withdraw to test if the vault blocks it. But we don't import the entire Gold Vault source code. That would be an overkill. So instead, we define this iVault interface to tell the compiler, hey, the target vault has these 3 functions and I want to interact with them. Once we declare this interface, we can treat the vault address as an instance of iVault and call those functions directly. Now we will go to writing the state variables very quickly. So the first would be an iVault public target vault. So this is going to be the address of the vault that we are targeting wrapped in the iVault interface. It tells us call the vault's public functions, like all of these functions that we've mentioned. Even if we don't have a full source code and it's like pointing a remote to the TV, we don't care how the TV is built internally, blah, blah, blah. Now, next would be, I have written it as capital. Yeah. So next would be address public owner, right? Again, it would be the address of the person who deployed the attacker contract, again, the mastermind, and only the owner is going to trigger or withdraw the stolen funds just to make sure random users can't hijack the contract once it's deployed. Then again, uint 256 public attack count. Now, this is also like to show that how many, like when we are doing a vulnerable withdraw, how many times did the attack actually happen, even if it was triggered only once, right? And then there would be like bool public attacking safe. Okay, so these are all the variables I can think of. Now, with the attacking safe, again, this is a flag which tracks which version of vault we are attacking. If the attacking safe is false, we're targeting the vulnerable withdraw. If it is true, we're testing safe withdraw and expecting it to fail very, very gracefully. So this helps us decide inside the receive function which method to call during the reentrancy loop. Okay, so now we'll go to writing the constructor. This should be done like a real quick. We say, hey, with the constructor, we would need the address. We're saying, okay, vault address, right? And we're saying, okay, the target vault that we have set should be equals to I vault and then this vault address. Okay, and then we're also saying that owner is equals to message dot sender, right? Now what happens when we deploy the gold thief, we pass in the address of the vault we want to attack. This could be any deployed contract that follows the iVault interface, and this line takes the address and tells the contract, this is the vault that we're going to talk to. Here's how we'll interact with it. And by casting an address as an iVault, we unlock all the ability to call, deposit, vulnerable withdraw, safe withdraw, all of those functions on the, target side of things. Okay. Now owner.message sender, again, this should be very, very clear for you. So we're saying, okay, now let's write a function where we're saying function attack vulnerable. We're saying, okay, external payable. Okay. Now what we check is whether message.sender is equals to owner. Okay. And we're saying only owner can call this function, right? Now, what is the other thing? We're saying we need to check if the message.value is greater than 1 ether, because that is how the person, gets the entry. There should be some balance. So you need a 1 ether to actually attack. If it's there, great. Need to have at least 1 ether to attack. Great. Right? Now what happens? We set the attacking safe to false, right? And we set the attack count to 0. Okay, right now we have not done any attacks, right? And then we say, hey, target vault dot deposit, right? And we're saying, value message dot value. Right? And yeah. And then we're saying target vault dot vulnerable withdraw. Okay, so we're using those functions. The first 2 lines are clear for you. The attacking safe false set to false and attack count is because we want the contract to make sure that it knows that this is a vulnerable attack, not a test against the safe version. And we reset the loop counter to start afresh. But what happens is we're depositing ETH into the vault with the target vault dot deposit line. So we are making a legitimate deposit into the vault. This updates our balance in the vault's internal mapping. making us eligible to withdraw the ETH. There was a mapping earlier, right? So that's why we're doing the deposit. And at this point, the vault is holding our 1 ETH safely, or so it thinks. Okay. Now this is the entry point which triggers the withdrawal, which says, hey, target vault dot vulnerable withdraw. Now we call the vault's vulnerable withdrawal function. This function checks our balance, sends us the ETH. Only after sets our balance to 0. And that's the mistake, because right when the vault sends us ETH, our contract's receive function gets triggered. Now, this is the point where we write that receive function. So generally, in all the contracts that we've been dealing with ETH, you see receive external payable. Yeah, receive external payable, but here there's a continuation. We say, hey, it's time you add the attack count by 1. And we say if attacking safe, okay? How did I? Yeah, so we're saying it's the vulnerable, attack mode. So we're saying not attacking safe and address of target vault dot balance is greater than equals to 1 ether and attack count is less than 5. What you have to do is target vault dot vulnerable withdraw. Okay, so if you are in the vulnerable attack mode, we check if the vault still has ETH to steal. We check if we haven't hit our attack loop limit, which we have set as 5 in this case. So if you have 10 ETH at once, if you are doing a vulnerable attack, 5 ETH will be gone. Okay, it runs 5 times. And if both checks pass, we attack again. So this is the reentrancy loop in action. Vault sends us ETH, triggers receive recalls vulnerable withdraw here, and vault sends us more ETH, triggers receive again, and so on and so on. So each time the vault still thinks we haven't withdrawn because it hasn't updated our, wallet till now, right? And if you're testing the safe vault, we're saying if attacking safe, target vault dot safe withdraw. Okay, so what happens here is in safe mode, we try to re-enter the safe withdraw function, but it fails. Why? Because the non-reentrant modifier is in place. The moment we try to re-enter, it detects the function is already running and it blocks us immediately. So the attack dies right there and no further funds are sent to us. Okay, so this target vault.safe withdraw is bound to fail. Okay, now we're going to write the attack safe function. Okay, so we're saying function attack safe. Okay, we're saying external payable. Okay, checking require message dot sender equals to owner, and this time I'll write a shorter message only owner. Okay, and we're saying, okay, can you check require message dot value is greater than equals to 1 ether, since we need at least one. Now what happens? Attacking safe is set to true and attack count is set to 0. Okay. Now target vault dot deposit, right? Now depositing a value is message dot value. Again, we are doing the deposit because we want it to mapping, and then we say target vault dot save withdraw. This will fail. This is bound to fail due to the reentrancy attack. And this function is meant to simulate the same attack strategy, but this time it targets the secure version of the vault, which is safe withdraw, so that we can show what is the difference here that we're talking about. And because it's well protected, right? And let us understand how did this happen. Is that just like in attack vulnerable, we check that the function is called by the attacker, which is the owner, requires at least 1 ETH. Same, set the attacking safe flag to true, so the fallback knows that we're testing the safe path, and reset the attack counter, right? Now, as usual, deposit ETH into the vault, right? Target vault deposit, again, I've already mentioned. Now, with target vault.safe withdraw is where the difference kicks in. When safe withdraw is called, the vault checks our balance. It sets our balance to 0. It tries to send ETH back to us. The receive function in GoldThief is triggered, and then we try to re-enter by calling safe withdraw again from inside receive. But this time we hit a wall. The moment we try to re-enter safe withdraw, the nonReentrant modifier checks the status flag and sees that the function is already in progress, and it will immediately throw an error that reentrant call blocked. And that's it. The attack fails before it can even start. No second entry, no loop, no theft, just a clean, hard stop, right? Now again, this is more like a proof of security. It shows that just with a few extra lines of protection like reentrancy guards. Yeah. So we were saying, why is this important? Is because this function is a proof of security. It just shows that with just a few extra lines of protection, like reentrancy guards and good function order, we can stop serious vulnerabilities in their tracks. And it's just not good enough to, how to code smart contracts, but also how to protect them too. Now we're going to write two very cute little functions. One is steal loot, so that once the attack is done, this function lets the attacker withdraw all stolen ETH from the GoldThief contract into their personal wallet. And then there would be like a utility function thing, right? So let's just go function, steal loot. Okay, so we're saying this has to be external. Now again, require, okay, I'll just copy this. Require message.sender is equals to owner. So only owner can call this. And we're saying payable, we'll make the owner payable. Payable owner dot transfer address this dot balance. Okay, so then the thief can just withdraw it all in their personal wallet. Not external, external. Okay, great. And the other one would be a function, a get balance, which says, which is again a very utility kind of function. External, a view, returns what? uint 256. And we say, okay, return address this dot balance. Okay, that's it. So it's a simple read-only function. Now this contract, exactly shows how a reentrancy works and all of that. We'll show you how things are going to work here. So I'll compile this GoldThief.sol. I will copy the Gold Vault contract address because they're asking for the vault address, right? And we deploy. Okay. Now what happens is here with the deposit, I will give 10 ethers, suppose, right? We're saying 10 ethers deposit. Great. And gold balance for this address is going to be 10 ethers. Okay, now let's go to GoldThief. This is where all the magic happens. So we're going to attack count is here, get balance is 0, owner is this, target vault is our vault address. Now attack vulnerability is where things happen. So here you're supposed to provide 1 ether again. We were making the deposit so that we get into the mapping and we're able to withdraw ETH. right? Now you'll see how instantly it will, withdraw the 5 ETH. So I say attack vulnerable. Oh, I passed 1 Ether, right? 1 Ether, right? And I say attack vulnerable. Oh, so what we were doing wrong is initially I had to set it to 1 Ether, but we did not give an equals to here. So go to the attack vulnerable function and make sure that message.value is greater than equals to 1 Ether, then it will work. So you go here, you attack vulnerable. Oh, we'll have to redevelop it, sorry. So we compile this and we copy this address, we transact. Okay, great. Now we will take 1 Ether here and we do attack vulnerable, and you will see directly 5 ETH because we were calling it 5 times. So although it should be able to withdraw 1, right? So it was 10 ETH here. We deposited 1 ETH from the thief's vault. That is why it became 11. And then 5 ETH are just right here. Okay. And right now we have it as 88.99. Now if you steal loot, it will get to 93. So it is able to transfer all of that loot to the personal wallet of the attacker. Now again, I will try to do this one again, and I will say attack safe. Yeah, so once we are running the attack safe and I've given it as 1 Ether again, this will fail, ETH transfer will fail, because again, with attack safe, we were implementing something as a safe withdraw. So the vault will check our balance, it will set our balance to 0. It tries to send the ETH back to us, and the receive function in GoldThief is triggered. But then what happens is, when they try to re-enter the safe withdraw, the nonReentrant modifier checks the status flag and sees that the function is already in progress and the transfer would fail. So the attack fails before it can even start. Okay. Now, one thing that I also wanted to show you guys again was if I deposit 1 Ether here and I say attack vulnerable, again I get 5 ETH, and now the attacking count will suddenly be 5. Why? Because we set the loop limit to 5, and that is why, again, it's going safe. Okay, and this attacking safe was false. If you attack safe, this does not work. Now get balance 5, owner, target vault. So yeah, I think that's all, right? Great. Yeah. So that's pretty much it here. We've started with a very simple, deposit and withdraw system, which has now turned into a real world Solidity security lesson. And we saw how a tiny mistake like sending an ETH before updating the balance can open the door to, reentrancy attacks. And then we saw how a smart attacker could loop through your vault like Pac-Man, draining funds again and again and again until it empties your wallet. But with the right defenses, non-reentrant lock, updating state before interacting with external calls, we can completely shut down the exploit. And this is why writing smart contracts is really about not just building cool features, but making sure that they're rock solid and abuse proof. So whether you're building a dApp, a DeFi protocol, or the next Web3 FortKnox, remember, secure your gold. Reentrancy is real. On to the next contract. I'll see you on day 21, and we'll be dealing with some real world applications now. So till then, keep building, guys. Bye.